Thank you very much, Nick. I appreciate that. Yeah, so I was asked to come here and talk about some of the physics that I'm doing, and they wanted it to tie in with Science Literacy Week and the kickoff, which of course is oceans. So I'm actually doing something about neutrino fishing in the ocean. This is not generally how it's done, and also this is not me. So I'd want to make that clear. I mean, I don't say that this is beyond the scope of something I might have done in my past, but it was never recorded, so I've gotten away with it to this point. So as I said, what we're going to talk about is we're going to talk about looking for neutrinos and doing that in the ocean. So although this won't be a hugely science-packed talk, I kind of have to start out by talking about what are neutrinos. To some extent, it doesn't really matter for what I'm going to say, but neutrinos are kind of one of the incredibly important particles that go on, that actually exist in our model of how we understand the universe. So this is kind of the model of how we understand what makes up everything in the world. Neutrinos are down here. There's a couple of properties that they have which make them particularly both useful and vexing. So the first, obviously, these are elementary particles. These are some of the particles that make up everything. They're incredibly light. Those of you in the front row, probably not too much farther back, might be able to see that all the masses of the particles are listed here. The neutrinos really just have limits. We actually don't know what their masses are exactly. We know what they have to weigh less than, but we don't know what they are. So they're so light that we have a lot of trouble measuring them. They're also very weakly interacting. So what that means is that when a neutrino comes through, it is very unlikely to actually do anything except just keep going. There's all sorts of cool things I could put out there that, like, for example, I think the number is that the rule of thumb is that there's 100 trillion neutrinos passing through your body every second. But of course, they don't do anything, so it's not a big deal. If you want to stop a neutrino, the stopping distance is something like several light years of lead if you actually want to have them stop. So these are things that they just are very unlikely to interact. And really that leads to the last point. This makes them incredibly hard to detect. The fact that they don't want to interact means that we can't just build something and leave it there and hope that these do something inside of our detector, which is kind of what we actually do in the end, but we have to be very careful because of all these things. So I told you these are really hard to detect, so why in the world are we wasting all this time actually looking for them? And the reason that we're doing, or one of the reasons, and the reason that ties into the astronomy nature of this event, is that we can actually use neutrinos to look at things that are happening really far away. If you think about, there's some event, it's happening super far away, and you're trying to figure out what happened there. So of course, the first thing that you think about is you're going to use light. You're going to use your telescopes and that kind of thing. And that works pretty well for things that aren't too far away, that you can still see. But there's dust and there's things in the way, and all of that light gets obscured. It's hard to detect the light when you're on the ground, all of those things. So light is maybe not the best messenger for it. So if these things that are happening that you're trying to detect are really energetic, they're going to create a lot of other particles, and some of those are listed here. For example, if you're looking at really energetic photons, they're called gamma rays. So anything that happens if you have like supernovas or collapsing stars and that kind of thing, they produces a lot of gamma rays. So those are good. They're good in that they tend to travel in straight lines. They're very energetic. They're super easy to detect. The problem is they have the same thing that happens with light. Anything that's in the way, it blocks them, so we can't see them. The same event that's going on is probably generating lots of what are called cosmic rays, which are really just very energetic charged particles. And those are good. They're also easy to detect. But the problem is they tend to get bent by all the magnetic fields that are in between this event and you. So when you look at them, if you detect them over here on Earth, it looks like they're coming from a different place in the sky. For example, in this picture, you would think that you'd put this backwards and say that something happened out here, when in fact it happened up here. So it turns out those really aren't so good either. The one that you really can use is these neutrinos. So these neutrinos, as I said, they're really weakly interacting. They're very rare that anything's going to happen. So they're just going to shoot through everything. They're going to point straight back at where they came from. They're going to make it to your detector on Earth. All of the good stuff we want. Except, of course, that they're really hard to detect. But we can maybe do something with that. So what are the kind of things that you can study? I'm going to talk really briefly about a particular detector, but this was the very dramatic and very science fiction image that was produced for something that happened just last year. Well, it was just announced last year. One of the neutrino detectors that I actually work for detected an extremely high energy neutrino, and that detection was backed up with a lot of other telescopes around the world. So this is the kind of thing that we can get information from. This was the first thing, the first neutrino that had been detected that was outside of our galaxy, so an extragalactic neutrino. And we can get those by doing this, by actually, building our neutrino detector and looking for them. So I've kind of motivated a little bit of why look for neutrinos. The high energy ones, you can look for all the things that are happening out, way beyond that no other particle is going to work. If you have low energy neutrinos, you can have supernova that are happening, or you can look at stuff happening in the Earth. That's also something that's that can be very interesting. And then particle physics, which is a little more in my ballpark. One of the great things about neutrinos is we can actually get at energies that are higher than the LHC. So the LHC out there that was, billions and billions of dollars and all these countries put together cannot come close to the energy that these particles have as they come to Earth that we can detect. So it's a great way to actually study the particle physics of the particles themselves, and you can look for things that are beyond what we understand. So I have this picture here. What we know about neutrinos, we know there are 3 flavors. We know that they oscillate between flavors. If you walked here or drove here, you probably saw the 57 banners around that say Nobel Prize, Queen's University on them. So we're pretty sure at that point that these oscillate and that we understand that. But are there other flavors? There's a possibility that maybe we don't understand quite everything about them and there's something else going on. And then we can look at the neutrinos themselves, which is the area that I'm particularly interested in, looking at what the neutrinos do. And I just really like this shot from Minute Physics here because it is actually quite true. Neutrinos are super weird when you really stop to think about it. So how can we detect neutrinos? I've spent all this time telling you that they're super hard to detect, they're not going to interact, all of that stuff. Well, when I say they're not going to interact, that's not quite true. They're very unlikely to interact, but they can. But then how do we detect them? The trick with them is that we'll never actually see the neutrino itself. What we will see is we will see the things that interact with the neutrino. As the neutrino comes into our detector, what happens is it will interact, it will hit a particle, and it will generate a lot of other particles. And if they have enough energy, they'll be traveling faster than the speed of light in the medium that they're in. So I have to be really careful when I say things like that. They will be traveling faster than the speed of light in the medium they're in. Not faster than the speed of light in vacuum. That's still impossible, as far as I know, as far as anybody knows. But they'll be traveling faster than the speed of light in the medium they're in. And what happens is something that's analogous to what happens with a sonic boom. So you think about if you have your sonic boom and you have your plane generating some kind of sound regularly, if when you're stationary, it's just sending out waves the whole time, as you start to move in the direction you're going, the waves start to pile up at the beginning because you're actually moving into the waves as they're generating. Once you hit the speed of sound in this case, you're just generating waves all at the same point. And if you go faster than that, then you start to generate this cone. And something very analogous happens with light. It's called Cherenkov radiation. So what we're looking for is the Cherenkov radiation that's generated. And this shot is of a nuclear reactor, and that's actually Cherenkov radiation here. It has this really cool sci-fi type blue glow that happens around all this stuff, which just makes it all the more intriguing. So this is how we're going to detect neutrinos. So you've decided you want to be a neutrino physicist. I have done my job, and I've convinced you all that this is something you want to do. And you want to build your own neutrino detector. So how are you going to do it? Basically, you want to have a large target mass. The reason you want that is that you want a whole lot of chances for these neutrinos to interact. Because it's so rare, you want to get something as big as possible to make it likely that something's going to happen inside your detector. And water is perfect, right? We just saw this case with water generating Cherenkov radiation. You want to provide a very clear medium, because if you want to detect that light, you want it to be able to make it out of the interaction, and you want to be able to see it as you're in your detector itself. And you want to be a little bit shielded from stuff that's going on around you. We, of course, are being bombarded all the time with cosmic rays and muons and all this stuff from our atmosphere and from space, and you don't care about those. You want the neutrinos. So you want to be shielded from those. You might be able to see the picture in the back here is actually the snow detector. And they did all of these things, right? They had this giant sphere full of water. So they had this water that they were using as their target. They cleaned it all the time so that they had this very clear medium. And they were shielded by going 2 kilometers underground at SNOLAB. So that's the way that the snow detector worked and the way that they met all of these three. But you might say to yourself, do you really have to go down in a mine all the time and work like that? Isn't there somewhere that we can find this target that is there and it's ready for us to use? And people, of course, have thought about this, and somebody very clever a while ago said, absolutely. There's the South Pole. So there's this whole huge glacier down there full of, well, not full of water, made up of water, that is just sitting there waiting to be made into a neutrino detector. So, well, maybe that's not what it's really sitting there waiting to do, but as far as I was concerned, or as far as they were concerned, that's what it is. So this is the South Pole. There's a few points of interest. The pole itself, I believe, is over here and moving this way very slowly. This is the South Pole station where people stay. For the time that you can actually fly in, for the months during the year that you can, that's the skiway where you can get in and out on the plane. And this odd shape here is the footprint of the ICECUBE detector. So the ICECUBE detector, what we've done is we've actually put sensors down under the ice, and we're using the ice itself as the target. So if you could look underneath, it would look something like this. Of course, you can't. This is completely fictitious and a made-up picture. But it would look something like this, where you have long strings that have a light sensor on the bottom. And this light sensor is the one that's looking for that radiation generated by the particles. And there's a whole bunch of them down here. In fact, if you could look, kind of cut away the side, it looks something like this. So here's the top that I showed you, and the station, and the skiway. But then you go down about 1.5 kilometers, and then the detector itself starts in proper. So all of this area is instrumented with these light detectors, and it's there waiting for neutrinos to come in. This is an example of what happens, what we see when a neutrino comes in. So a neutrino has come in this way and has gone through. It has come this way. It's hit a particle somewhere out here, and the particles that it hit have gone through and generated light and made this big signature in the detector. So that's the way that we can actually detect neutrinos. So it seems pretty good. There are a few issues. Once you put those strings down in the ice, that's it. They're gone, right? We cannot get them out anymore. I mean, I guess, don't want to get political, but I guess climate change is doing its best to get them out for us. But that's not going to happen, hopefully, in my lifetime. So once you get things down there, they're not retrievable. You can't change anything about it. The other part is, like, folks, it's really far to the South Pole. To get to the South Pole takes a really long time, and it's really expensive to get to the South Pole. It is not expensive enough, apparently, this is a bit of an aside, but to stop someone from drinking a steam whistle right at the South Pole. So there was a group of Canadian tourists that went down, and this guy drank his steam whistle at the South Pole marker itself. So that was pretty impressive. I found that while I was preparing for this talk, so kudos to you, sir. But yeah, so this is one of the problems that we have. So there has to be a solution to this, right? There has to be something that we can do about all these problems. It doesn't have to be, the thing is, it doesn't have to be ice itself that we use. It could be water. And of course, there's lots of smart people out in the world, and people have thought of that. And in fact, there is a detector, kind of two detectors, in the Mediterranean that does exactly what ICECUBE does, but in water. So these are shots of the Antares detector and potentially the future CAN3net, where they have installed these sensors, the same thing that ICECUBE used, and they're using the water instead to look. That has a few different problems, of course, which I will get to later. One of the benefits is that you're in the Mediterranean, you're not at the South Pole, so I clearly have made some bad life choices in the projects that I work for, but there still are a few issues here. But when you're thinking about this, you're thinking, okay, well, all this needs then is this kind of water. And as we heard in the intro, Canada has a lot of water, right? So this seems straightforward. Why don't we just do this? Well, it turns out it's not quite that easy. One of the things so these projects are actually having a few problems. One of them are these connections that connect your strings to get power and data and all of that stuff transferred. That's really hard. If you're under 2 kilometers of water, with all that pressure down there and all of the things going on, it's incredibly hard, and these connectors are failing at an alarming rate. One of the difficulties is this one. When physicists design them, they are generally not designed all that well, so they are failing. And there has to be a solution to this problem because it just seems like a technical problem that we can get by. And it is. So fortunately, in Canada, we have this thing called Ocean Networks Canada. So what Ocean Networks Canada has done is they have this whole huge, basically this outline of this path which carries data and carries power and all that stuff. It's all laid across the floor of the ocean just off the coast of Victoria. So this is a University of Victoria group that gets together and they're doing monitoring of all of these different things out in this place. And so if you look here, I said we wanted about 2.5 kilometers of water above us. There's the Cascadia Basin, which is about 2.6 kilometers down, which is just about perfect for what we want to do. It has, there are a few things we have to work out, which I'm going to get into, not the least of which, apparently there's an American submarine base somewhere in here that they really don't want us putting a lot of instrumentation out here, but we think we've worked our way past that. So the ONC, this group, is willing to work with us in order to try to make this detector happen. So what can they offer? They can offer, first of all, the coolest logo that I've ever seen. But in terms of science, they can offer this Neptune observatory. So this is the one that's out there. It was finished back about 10 years ago. It's this huge loop that has all of this cable that goes out and power and all that stuff. But really, the important part is this one. It's designed for long-lived, highly reliable underwater operations. So the kind of thing that physicists don't design for, these guys are thinking about it all the time, and they're willing to let us use it. So it's turned out to be an incredibly good pairing with them. So what have we done? What we have done is we have actually put some sensors down under there to see what's going on. In order to see if this is feasible, we need to understand a few things about the water itself. And so what we did was we put some sensors down there, this STRAW digital optical module, so it's the strings for absorption length in water. And what we're trying to measure is how far can light go? Remember I told you we need a lot of water? Yeah, okay, we've got lots of water, that was easy. But the water needs to be clean and we need to be able to see the light in this water. So that's what these were set up to do. So we put down 2 of these strings and we were able to try to figure out how that's going. And the way that we did that was we have these 2 strings, and we're able to use one of these strings as an emitter, and then look to see what we detected on the other side, to see how much light makes it across. And doing that lets us kind of try to figure out how clean the water is, how appropriate this is for our use. And so this has been installed for a little while. You can see that there's a timeline here where by about June of 2018, we deployed it. So we've had these things out there. They've been installed. These are shots of the ONC people doing the installation for us, which is pretty cool. Again, they were very wise and didn't allow any physicists to be on the boat when they did it, but they took care of the whole thing. So basically what they have is they have these big cable reels with all of our sensors on them. You can see a couple of the sensors here that are on the cable reels. And they reel out the cable, they set it down, but then they need to actually attach it to the infrastructure at the bottom. So they have a little ROV type thing that goes down and grabs it, and then we'll take it down and attach it down to the thing at the bottom. And this whole process is incredibly cool and looks really neat. You get really neat shots of this thing going down to the bottom and connecting things up, and this little robot working, and it's just kind of the coolest thing ever. Speaking as someone who doesn't get to do things with the ocean very much, this I was really impressed with. But anyway, so yeah, we put it out in June of 2018. Took a little time to get us to figure out what was going on, and then we got some data from it near the end of 2018. And so, what have we learned? So we've learned essentially 3 important things which are on these graphs here, which I will just go through very briefly. The first thing that we learned is that sediment is maybe not a problem so far. So one of the concerns that we have is that if these optical sensors are down there and there's a lot of stuff floating around in the water, it's going to kind of gunk out these sensors, get on top of them, and make them really dirty. And so this kind of graph shows the output, and you can see that over the scale of here, which I think is February to June or something like that, over that time, it didn't really degrade the performance very much. Now, you may be saying February to June is not very long, and that's true, But when we talked to the people at ONC, they actually have a solution. They said that we have this special cleaning device that we use that we can send down with the ROV, and it's all these technical terms and blah, blah, blah. And it didn't turn out until they gave their talk that they were just messing with us. They put a toilet brush on the end of the ROV and go down and scrape the things off. So it's their incredibly technical device. It probably cost $1.29 at the dollar store, and that's saving our detectors. But so far, we think that we're not going to need a lot of toilet brush application, so we're probably going to be good. The second thing we learned is that the water is probably clear enough. I don't know if you can make this out. There's several different telescopes, neutrino telescopes that are on here, and the quality of their water. And so the x-axis is just the wavelength, and the y-axis is how much we can see. So all of them are roughly in the same ballpark. So we are roughly the same clarity as the ones in the Mediterranean, which have been working when they actually work. So we're pretty sure that the water is clear enough. We're good that way. The last piece was something that we also weren't expecting, but the biologists had told us to expect from the beginning, is that we have bioluminescence, and the bioluminescence is correlated to the current. So what you can see here, this top plot is the rate in our sensors. So you can see it goes up and down. And the bottom plot is the current and the measured current. So exactly in line with the current, we get this bioluminescence in our sensors. We weren't expecting this. We know that the people in the Mediterranean had a lot of trouble with bioluminescent fish, but at this depth and in this water, we weren't expecting any fish. So it turns out it's not fish. It's these little things whose name completely escapes me, but they look like little bags, basically, and they're tiny, just microscopic organisms. And what happens is they travel in these giant packs, and they just float through the water. They propel themselves by using their little bag structure, and after they hit something, they give off a flash of light, and that tells the other little bags to steer around where that is. So first of all, that was pretty neat, but it means that if we get this current happening, these things are smacking into our sensors and lighting up, which is exactly what we don't necessarily want. So we think that we can filter this out. The wavelength of the light is slightly different than the wavelength of the Cherenkov radiation, so we're pretty sure we can get rid of it. But this is something that we are going to have to deal with. Fortunately, we think that by looking for coincidence between different sensors, we're going to be able to get rid of a lot of this. These are very local. They don't flash very brightly when they run into stuff. So we think we can handle this, but it's just something that was really interesting that we learned as we were doing this. So what are the next steps? So I told you that was STRAW. That was whatever I said the acronym was for, something about the transmission in water and absorption in water. So we're going on and we're doing the next phase, which we're calling unimaginatively STRAW-B. So what we want to do here is we want to learn a little bit more about the water, and we want to actually start to do some physics a little bit with it. So you can see this is the same thing that we have. We have the connection down to the bottom. We have a string full of a bunch of things, but we're putting a few different items on these strings. Rather than just looking for transmission across, we're also going to put in LiDAR. So we're going to see if we can actually figure out how these things move, especially how they move relative to each other. Because, of course, once they're just fixed at the bottom, the current takes them, and these strings will go all over the place. So we're trying to get a handle on that. We're looking at the spectrum that we get. So we have a PMT that's going to be able to break it up into different wavelengths of light. We're actually going to start to look for muons, so to see if we can understand how many muons are coming in, what the rate is. And then we're going to maybe put some pretty experimental new sensors in here called a wavelength shifting optical module, which I can get into if you want later on, but it's some pretty neat technology we're going to try to do. So the timeline for this, we're looking in testing this year. We have all of these built except for this one, but we think it's going to make it. And then we're going in the summer next year. We are not going to. ONC is going to deploy it for us. So then we'll get a whole lot more information about what's going on and what is actually happening down there and how suitable it is for us to plan there. And so all of that leads into the big experiment that we're talking about doing, which we've called P-ONE, for the Pacific Ocean Neutrino Explorer. And so what P-ONE is it is essentially a bunch of these strings gathered together, something like the IceCube detector. So we would be able to have either rings of these strings or possibly different shapes. I'll show you a slightly different shape in a minute of these strings and be able to use those to do the physics that we really want to do. So this is just a shot of the two different kind of sensors that we have on here. and a potential, if the funding agencies are kind to us, we can actually make this modular and start to make this really big and instrument a lot of water, leading us back into getting a lot of events. So the timeline here, this is our proposal. We're in 2019. We're talking about straw B in 2020. And then once we get our money from CFI, if we get our money from CFI, we can start to build things. And then in kind of the 2022, 2023 area, we'd be ready to put this whole thing down there. So the grand plan is basically to have a kind of global neutrino observatory. So what we would do is we would be able to work with a lot of the other neutrino detectors there to really understand the neutrino fluxes. So this is us at ONC up in Canada. Here's the one I told you about, KM3net. There's one in Russia called GVD, and then ICECUBE down at the South Pole. So all of these would kind of form this, Voltron-like supergroup of neutrino detectors that we would all work together in order to try to get really sensitive. And one of the reasons we want to do that is kind of illustrated on this really dense plot, which I don't want to spend a whole lot of time on. But basically what happens is, if you're looking for neutrinos of high energy, you can't actually look for neutrinos that have gone all the way through the Earth. For complicated reasons, when neutrinos get really energetic, they get stopped by the Earth. So you can only have a little bit of Earth in your path. So if you were to plot out where all the different telescopes can see on the kind of galactic coordinates, you can see that this is what they would see. So for example, you can see these are the IceCube lines here. IceCube is down at the bottom, so they have that angle that goes around that they can actually see things from. But once you start to add together all the different observatories, you start to have a lot of coverage. So anything that happens, we can see what's going on. And if there are sources of high-energy neutrinos out there, we would be able to pinpoint them with good either coverage or confirmation from several different telescopes, which is exactly what we would like in science. You'd always like to have your results confirmed. So this is kind of the grand plan of world domination in the neutrino area. So I think the bottom line, what I'm saying here, is that you should definitely keep watching. We're working on doing this. We're constructing and commissioning in the near future. You can see what we've got here, what I'm showing, is a slightly different configuration of our strings. If we wanted to make them kind of longer or wider, but not as long, and we've done some simulations of what those could see, and they end up being here. But I think there's really interesting stuff that's going to happen probably soon with this group. And this is just a list of the people that are involved. So it's multinational. We have Michigan State is involved in kicking in a lot of money. And TUM in Munich is there. And then there's the Canadian group. So the University of Alberta, Simon Fraser, us, me at Queen's, and ONC. So it's this team that's coming together in order to make this cool new neutrino detection experiment happen. And we hope that soon we'll have something really neat to say and let you all know. So thank you.